Now let's look at the first example problem. It's called a binary calculator. So let's read so I will not read the problem description here. You can read it yourself. The problem description explains a binary number and 2's complement, just like I did in the previous video. So the main goal of this problem is to, I guess there are two goals. One is to show how to process a binary number and also to parse the expression and then compute its value. And the second is to show the internal bit patterns for the binary number. So you actually see the 2's complement that we described earlier. So in this problem, each input had a number of lines. Each line had one expression, and the expression of this form. So essentially, number plus number minus number and equals. So it's an arithmetic expression, but for simplicity, I don't allow parentheses and I don't allow multiplication and division, because if I want to parse that, the natural way is to use a stack, which is something that I have not covered. So here, just with just addition, subtraction, and without the parentheses, we can just process each number as they come. So we need to process a lot of this expression, and then we are computing their value. And for the output format, we want to both see the decimal value and also the internal bit patterns in the as represented in the computer. So let's look at so some examples. So 1 plus 1, so that should be and all these numbers are binary. So 1 plus 1 is 2. So that's binary represented as all 0 for, and ended with 1 0. And this is 1011, that's 11 plus 5 minus 3, so that's 13. So 13 is 1101, 8 plus 4 plus 1. So then it's represented this way. So the next one, all this added together is just all ones in all the lower 8 bits, and that's 2 to the 8 minus 1. No, sorry, 2 to the 9 minus 1. No, yeah, okay. So this is 9-bit one, so there's a 1 here. So this is 2 to the 9 minus 1, so 511. And the next one is -1. So this is the internal representation, -2. And the last one, what I want to show is when we minus this number, so the starting 0 doesn't really matter. So the first ones will become zeros. So here there's 3 ones, it becomes 3 zeros, and then the next the zeros will become ones, and until the last group of ones. So then when we do, for example, 1 0 0 minus 1 1, what we get is going to be 0 1. So that's basically what happens. And ending trailing zeros will maintain unchanged. So this in binary subtraction is almost the bit changes in this fashion. So now let's look at the code. So I also vary the input file format a little bit. So instead of telling you how many lines there are, now I just tell you read until the end. So we can do that by using this. So this reading into a string, this expression actually has a value. So the value will be true if only if reading succeeds. So if when you try to read and there's nothing for you to read, you reach the end of the file, then this will give you a 0 value. So by using this, we will be staying in the loop so long as we actually read something, read a string. So then I first parse the first number. So the first string that I read will be the first number here. So like this one here. So I want to turn that string into a number. So I can do that by writing my own code, just similar to the last topic when we do parsing integer, parsing parsing a floating point number. So the same logic can be used to convert a string into a binary string into an actual number. Each time we multiply by 10, we just need to multiply by 2. But there's functions, library function for doing that. So here I just use the library function, show you the names of the function. So this is S2I means a string to integer. So this is a C++ standard function. So you take a string, and then the general form is take 3 arguments. So I think this can indicate starting from which position to read. For our purpose, it doesn't. We want to start from beginning, so this we can use this keyword null pointer. And the last one represents the base. So we can tell this library function to parse base 2, or we can do other base as well. So so we first read in the first number and store that, and then the loop handles this this operation. So I handle this by pair. So for example, after reading this number, I will handle the next group, add something, next group, subtract something until I see an equal sign, and then I will get out. So the first thing I do is to check the equal sign. So compare this token with a string of equal. So this compare function will return. I think it's a 0 when they're equal. When it's larger than, it will return a number bigger than 0, probably 1. And when this string comes before this, it will return a value less than 0. So here, if it's equal, then I break. So then that means we've seen equality. So then at this point, this answer stores the result. So I just want to print it out. But in order to print this binary bit pattern here, I first convert this answer into a what's known as a bit set. So bit set is a STL class. So it's a store a set of bits, and so a integer that has 32 bit can be interpreted as a storage for a 32 member bit set. So this is what we are doing is we create a bit set object using the integer value and interpret that integer value as 32-bit bit set. And then I convert that bit set to string. This will give us the binary string. So all this 0, 0, 0, 0, 0, 1, 0. So because I want to make the output a little bit easier to see, I want every 8-bit, I want to white space. And yeah, I guess one thing that I didn't explicitly say, but I assume most of you already know, is 8-bit is a group called a byte in computer. So that's widely used unit for storage. So we often talk about how many byte, whether we're talking about main memory or hard drive. So integer use 4 bytes. So 32-bit is 4 bytes. So here I want to print each byte separately, so it's a little bit easier to read. So I do that by taking the string and then chop it up into 4 substrings, and then when I print them, I add white space in between. So that's when I see a equality. If I don't see a equality, then this token will be either plus or minus. So unless the input doesn't satisfy the specification, which we don't need to worry about. So then I read the next number. So the next number is no, yeah. I read that next number as a string, and then I parse that into a integer. I treat that as a binary string. So here I show a slightly different way of using the parsing a string into a number. So in fact, this function is originally in C standard library, so it's inherited in C++. And STOI is a new thing introduced in C++, but actually STOI just called this function to do the job. So they are more or less equivalent. And because this is a C function, it needs to take input as a C string. So in C, a string is just a array of characters, and a string will end when we see a 0 character. So not the ASCII 0, which is actually non-zero, but the value all 0. So essentially a byte with everything is 0. This byte. If we see this byte at the end, then that's the end of a string. So and the C++ string is different. C++ string has a length, so it's a class that has in addition to the array for storing the characters, it also have a length. So because this function takes the C string, so we need to get the C string from the C++ string, STL string. So I do X is STL string. It's a string type. And we call this a C string function to get the corresponding C string. So this parse this into a number. And then depending on whether the token is a plus or minus, so if token is a plus, so here I use another way to compare. I directly use a double equal. So this double equal operator is overloaded by the string class. So essentially the string class re-implemented this double equal to actually check, do string comparison. And for those of you who will be programming in Java in near future, so I want to warn you, if you do double equal comparison in Java for string, you likely will get something that's wrong, because in Java, each string is an object, and the double equal by default, they have to be exactly the same object. So whether they are containing the same string doesn't really matter. So then things that you expect to be the same string, but in the memory, they're actually two separate objects. They happen to contain the same string, just like two variables happen to contain the same number, the same value. So that could happen. So yeah, just if you're using Java, be really careful when you use double equal to compare string or in fact any object. But in C++, these are when for standard library, when it makes sense, this double equal is overloaded, so using it is fine. So if it's plus, then I add the value. Otherwise, it should be minus. There really shouldn't be anything else. But I added the code to do error checking. Just make sure that the test case I generated actually follow the specification. So here, so again, here I'm using compare. So, but instead of direct comparing to 0, I'm just saying that if it's not true, because when this compare is true, it gives a 0, and negation of 0 is true. So this is equivalent to this. So yeah, if it's a minus sign, I do minus. Otherwise, I print the error message. So I think that's it for the code. Let's just quickly take a look at the slides. Yeah, so the bit set, I use the bit set here is only for showing the internal bit patterns, so that I don't need to write actual code to do that. So using bitset is not needed for any problem in this topic, and in fact in the next two topics. So you don't need that in CP0. In fact, I don't think you will need that in CP1 or 2 either. So it's a little bit specialized class. So and here are links to the document on STOI and TRTOL. You can read that if you want. Okay.